Beneath the crystalline waters and the jagged rim of Crater Lake, a place so beautiful, you'd swear it was carved by the gods, not forged by chaos. A silent force is at work. The headlines are not screaming it yet. Tourists still gather by the shore, marveling at the endless blue, snapping photos against the mirror-calm surface. Fishermen cast their lines for trout. Hikers circle the caldera, unaware of the slow changes that may be happening deep beneath their feet. Yet, beneath Oregon's most famous lake, the mood among geologists has shifted. The pressure inside the caldera, once believed to be relatively stable, appears to be showing subtle signs of change. This development is capturing the attention of researchers and is contributing to a growing sense of urgency about volcanic activity across the broader Pacific Northwest region. The United States Geological Survey's instruments, as well as those operated by research teams from institutions across the West, are continuously monitoring the area, scrutinizing every slight ground movement and trace gas emission. For now, the signs are subtle: slight ground deformation, tiny fluctuations in gas levels, faint seismic signals. This is not the kind of drama that makes for front-page news. But among scientists, these small shifts are starting to form a pattern that merits attention. Globally, the world is watching increased volcanic activity. Mexico's Popocatépetl, various peaks across Alaska, and the undersea axial seamount off the Oregon coast, all displaying signs of unrest or predicted future eruptions. Yet here, beneath one of the United States' most iconic lakes, the clues are far quieter, easily overlooked by all but the most attentive eyes. What is Crater Lake signaling? Is this simply the natural settling of an ancient caldera, or the early signs of a more significant awakening? What secrets does this blue abyss hold, and how close are we to understanding them? Deep pressure, invisible uprising. At first glance, Crater Lake seems eternally peaceful. The water's color, a blue so deep it seems otherworldly, covers what remains of Mount Mazama, a volcano whose collapse formed the lake nearly 7,700 years ago. Every moment of calm is the result of millennia of volcanic violence finally subsiding. But recently, a network of sensors positioned around the rim and the caldera interior have registered trends that, while minor, have captured expert curiosity. Slight ground deformation, sometimes only measurable in millimeters, has been detected. Changes are sometimes intermittent and localized, but taken together, they provide the first hints of something stirring beneath the calm surface. The culprit? Pressure. Not the kind heralding an imminent eruption, but a slow, steady uptick that may indicate the movement of fluids or the inflation of magma chambers deep below the surface. GPS and INSAR satellite tools are showing a minor but detectable pattern of ground uplift. Some areas rising ever so slightly, likely in response to changes deep within the caldera. The uplift does not currently suggest a crisis, but it emphasizes that Crater Lake is a living system, not a fossilized remnant. The pattern of inflation, most noticeable along the western and southern margins, matches areas where the ancient volcanoes' fractures and faults converge. Similar patterns of inflation, now and in the past, have been observed at other volcanoes like Italy's Campi Flegrei or Chile's Laguna del Maule. There, persistent uplift often coincided with changes in below-ground heat and fluid pathways, not necessarily with eruptive crises. Thermal imaging and satellite data, when analyzed together, suggest subtle increases in localized heat flux. These changes are only distinguishable from normal background variation when data are averaged over time and space. For now, these zones of heat don't register as anything extraordinary at the surface. but they are reminders that energy is quietly being redistributed below. Crater Lake, by scientific consensus, is not on the verge of eruption, but the ground is moving. The signals, however faint, are being recorded, and science is always cautious in the face of such quiet persistence. How much force is stored beneath this basin, and what would it take to release it? Signals in the silence, subtle warnings from the deep pressure, is only one aspect of the volcanic story. Researchers keep a careful watch over gas emissions, water chemistry, and small seismic events in and around the lake. Crater Lake's geothermal and volcanic history means that vents and seeps are part of its natural environment, but changes in these can be significant. Sensors, particularly those along the southern and western flanks, have reported sporadic upticks in carbon dioxide emissions over the last year, as well as trace levels of sulfur compounds. These values remain modest and generally within natural fluctuations, but are being monitored for sustained departure from previous baseline readings. In volcanic lakes around the world, such shifts sometimes correspond to changes in magma movement or hydrothermal activity deep below. Lake water, regularly sampled at multiple depths and locations, including near the Wizard Island fumarole field, occasionally shows minor variations in dissolved minerals and temperature profiles near geothermal seeps. Such changes are usually interpreted as evidence for subtle shifts in hydrothermal circulation or water-rock interactions, driven by changes in the subsurface heat flow. So far, these shifts are far below the threshold for any public safety concern, but they are dutifully logged and studied as potential early warning indicators. Crater Lake is one of the most seismically quiet calderas in the western United States, but advances in seismic technology mean that even the faintest micro-earthquakes can now be detected. Over the past year, several very small seismic clusters, too weak to be felt, have been observed at depth beneath the caldera. The nature of these events appears consistent with minor adjustments along ancient fault lines or fluid movement below the lake floor. No pattern points to rising magma, but even background chatter is valuable data. Each of these subtle shifts is prompting the same discussion in scientific circles. Are we seeing only the standard living noise of a dynamic volcanic system? Or are these coherent signals hinting at the beginnings of a reawakening? Heat from the abyss, thermal clues, and hidden reservoirs. Temperature shifts offer another line of investigation into the heart of Crater Lake's complex system. Over the past year, new tools, especially airborne and waterborne infrared sensors, have been utilized to map the thermal profile of the caldera in unprecedented detail. Thermal imaging regularly targets the mineralized vent fields above and around Wizard Island and other notable hydrothermal locations within the caldera. Analysis of these data sets reveal a thermal profile that remains largely stable, as one would expect in a volcanic system believed to be dormant. Small anomalies are identified, but they fluctuate seasonally and often co-vary with solar heating and water inflow, rather than providing unambiguous evidence of volcanic reactivation. Critical review by USGS and independent researchers has found no persistent or alarming thermal hotspots indicative of imminent volcanic danger. Most findings align with the background geothermal characteristics typical of Crater Lake's long post-eruption cooling trend. Beneath the surface, geophysical methods such as magnetotelluric (MT) surveys are occasionally used to investigate the distribution of fluids, rock types, and heat sources at depth. The presence of low resistivity zones, suggestive of wet, clay-rich rocks formed through ancient hydrothermal activity, confirms that the lake is still affected by legacy features from its violent origin. Thus far, the areas with slightly elevated temperatures correspond with these historically altered substrates, rather than with new upwelling of deep magmatic fluids. For now, both the surface and subsurface thermal data reinforce the picture of a mostly quiet volcanic system, one that is continuously monitored, but not currently on the edge of dramatic change. Mineral records. The stones remember. In addition to monitoring ongoing processes, geologists study Crater Lake's mineral record for evidence of past events and long-term trends. Core samples drilled from the caldera rim and surrounding slopes reveal a story of episodic eruptions, hydrothermal alteration, and intermittent recharge by fluids from below. Scientific drilling over the past decades, much of it for research and hazard assessment, has recovered sequences of volcanic ash, altered lava, and hydrothermal minerals, zones where clays have transformed at high temperature, especially the presence of minerals like elite, indicate periods of sustained heat. Such features are not new or unexpected, and they reflect thousands of years of natural cooling and water-rock interaction since Mount Mazama's collapse. Traces of elements like lithium, boron, and arsenic are found in some hydrothermally altered layers. Their presence is normal for calderas with histories as dramatic and as water-rich as Crater Lake. Isotopic analyses of minerals provide more detail, often showing signatures consistent with water that originated at depth, interacted with hot rocks or magma, and then slowly made its way toward the surface. Yet these records suggest active processes from the distant past more than ongoing surface danger. Taken together, the stone and mineral record points to a system presently in equilibrium, but responsive, one with a history of violence, but currently at peace. Anatomy of a chain reaction. Volcanoes in conversation. Crater Lake is only one part of a much larger geologic story that stretches across the Pacific Northwest and along the Pacific Rim. The region's volcanoes, including the axial seamount off the Oregon coast, Alaska's volcanic arc, and Mexico's Popocatépetl, share tectonic ancestry, formed by the ongoing subduction and collision of oceanic and continental plates. In 2025, scientists are giving renewed attention to possible connections between volcanoes that were once considered largely independent. The axial seamount, for instance, is forecast to erupt sometime in the next year, according to credible predictions based on decades of precise seafloor pressure sensors. In Alaska, increased gas emissions from certain volcanoes have prompted reports that an eruption is likely, and regular monitoring continues. Popocatépetl, one of North America's most consistently active volcanoes, serves as a reminder of how even long-dormant systems can awaken. Geophysicists know that tectonic stresses can transmit over large distances, and that major volcanic and seismic events sometimes occur in regional clusters. Gravity and satellite observations show that the subduction and extension zones underlying the Pacific Northwest create complex patterns of stress and heat flow. While it is not established that events at axial seamount, Alaska, or Crater Lake are directly linked in real time, the system is interconnected in a broad geodynamic sense. The possibility of so-called volcanic chain reactions is a subject of scientific debate. While historical records show that volcanoes within a region may have intermittent bouts of activity, true cascade effects, where one eruption triggers another, are considered highly unlikely given our current understanding. Instead, what is observed is a background readiness, where several systems may respond to shared changes in regional stress or mantle processes, though their precise timing remains independent. The larger picture is this: the entire western margin of North America is geologically alive, and every volcano is part of a greater tectonic landscape, one in which slow shifts and sudden eruptions are inevitable, but rarely synchronized. To further complicate matters, ongoing advances in satellite geodesy, such as INSAR, interferometric synthetic aperture radar, are revealing subtle inflation patterns around dormant volcanoes once thought completely quiet. Some of these patterns, like those recently recorded near Mount Shasta and Medicine Lake, are consistent with magma recharge at depth, though not necessarily a sign of impending eruption. The takeaway is that volcanoes are constantly evolving, even when no activity is visible at the surface. Moreover, beneath the Pacific Northwest lies the Cascadia subduction zone, a megathrust fault capable of producing magnitude 9.0 earthquakes and massive tsunamis. While its seismic threat garners more attention, it also plays a role in regional volcanism by continuously introducing water-rich oceanic crust deep beneath the continent. This process lowers the melting point of the mantle, generating magma that feeds the Cascade volcanoes. In that sense, Crater Lake, Mount St. Helens, Mount Rainier, and even more obscure peaks like Glacier Peak are not isolated features. They are expressions of deep Earth dynamics, a volatile balance of subduction, melting, uplift, and eruption. Understanding these systems not as standalone threats, but as parts of a tectonic orchestra, is key to anticipating how this geologically restless region may evolve in the years to come. Cascading consequences. If the blue giant breaks, what would happen if Crater Lake underwent a period of significant unrest, or, in a more dramatic scenario, erupted again? First, it is important to emphasize, experts agree that there is no reliable sign that such an eruption is imminent or even likely in the foreseeable future. The most probable future scenarios involve continued monitoring, periodic detection of minor changes, and further refinement of eruption forecasting tools. However, because Crater Lake represents a system that has erupted catastrophically in the past, the hazards are well studied, and preparedness is an ongoing priority. In any volcanic system of this scale, possible consequences of significant unrest include increased microseismicity, local ground deformation, heightened gas emissions, and hydrothermal explosions. For Crater Lake, even a moderate event, such as a phreatic, steam-driven eruption, could disturb the lake's chemistry, produce localized ash, and, in extreme cases, temporarily disrupt visitor access and the park's ecology. A large magmatic eruption on the scale of Mount Mazama's ancient collapse would have widespread consequences, including regional ashfall, air and water contamination, and possible impacts on agriculture and infrastructure. The last such event occurred nearly 8,000 years ago and reshaped the landscape for hundreds of kilometers. However, this level of eruption is not expected in any current forecasting models. Even in the absence of catastrophic events, the mere fact of living near or on a volcanic system carries a certain degree of uncertainty. Communities in the Pacific Northwest are well aware of this risk, as the 1980 eruption of Mount St. Helens underscored. Preparation, hazard mapping, and monitoring are part of life in volcanic regions. In the event of elevated activity at Crater Lake, emergency planners would rely on the best available science to inform decisions about access, evacuation, and resource management. For now, however, Crater Lake's story remains rooted in careful vigilance, not urgency. shaping the future. Science at the threshold. What comes next for Crater Lake and the broader volcano watching community is a story of ongoing research, preparedness, and humility before nature's complexity. Teams from universities, government agencies, and local tribes continuously gather and analyze data on seismicity, gas emissions, ground deformation, water chemistry, and temperature. This information is incorporated into increasingly sophisticated models designed to provide early warning if risk increases. Machine learning and advanced simulations now supplement traditional techniques, hunting for hidden correlations and subtle warning signs. Despite these advances, all experts agree. Volcano forecasting is an uncertain science, and most periods of minor unrest pass without major consequence. The hope is that by combining many lines of observation, satellite, drone, ground, and underwater sensor networks, any future escalation in risk will be detected early enough to respond effectively. Policymakers, guided by scientific reports, continue to update emergency protocols, public education campaigns, and resource plans. Tribal leaders add depth to the scientific account, sharing historical and oral records that remind all involved of the cyclical nature of volcanic activity in the region. For the communities nearby, life goes on. The enduring lesson is to remain curious, attentive, and ready, to value science and preparedness as the means of living safely in a dynamic landscape. Each new observation, each uptick in a chart or spike in a gas sensor is carefully evaluated and put in context. At Crater Lake and beyond, these observations are not the harbingers of doom, but the subtle signals of a restless planet, one whose future, while uncertain, is watched more closely now than ever before. One question remains, one that only time and vigilance can answer. When the Earth stirs quietly beneath Crater Lake, will its story be one of routine cycles or an extraordinary new chapter? If you want to see what comes next in America's hidden frontiers, if you want to be the first to know what the Earth is whispering, rumbling, or shifting to say, make sure you're here with us. Like this video if you want ongoing updates about the Pacific Northwest's most fascinating volcanoes. Subscribe so you never miss a discovery, and tell us in the comments, do you believe these are only gentle ripples in an ancient arc, or the first signs of a future transformation? Stay curious, stay attentive, for the land beneath Crater Lake is part of a world that is always in motion. And so, too, must be our watchfulness.